All right, we're doing assignment number 17, starting with problem number 13. It says, determine the open intervals, that just means parentheses only, on which the graph is concave upward or concave downward. So the possible inflection points are where the second derivative is equal to 0 or undefined. So you can either use quotient rule or product rule here. I'm going to use quotient rule. F prime x is equal to low d high minus high d low all over low. And because we need to take the derivative of this, we should simplify what we can. So you can either factor a 2x out, or you can distribute the 2x's through and combine like terms. I'm going to distribute and see what happens. So when you distribute, think of this as like a negative 2x that you're taking through to these two parts. All right, so 2x to the third minus 2x. So negative 2x times x squared is minus 2x to the third. Then negative 2x times 1 is minus 2x. Nothing to do here. So this is still f prime x. So the 2x to the thirds are canceling. I'm getting negative 4x over x squared minus 1 squared. All right, and then again, we can do quotient rule, or you can rewrite this and do product rule, but I need to get the second derivative. I'll just use quotient rule again. So low d high minus high d low. Now be careful here. So you have a power rule and a chain rule. So its power rule is 2 times this thing to the first power. And then the derivative of x squared minus 1 is 2x. Over low. So when you square this quantity, you get x squared minus 1. Now it's to the fourth. And because we need to figure out when is f double prime equal to 0, I do need to clean up the top a little bit. So I'm just going to keep this out here. So negative 4 times x squared minus 1 squared. And then this can be plus 4x. And this is 4x. So plus 4x times x squared minus 1. So I just want to clean this up a bit. So plus 16x squared times x squared minus 1. And then it's still over x squared minus 1 to the fourth. All right, now we should factor this a little bit in the top. I see a GCF that can come out. Both of these have a minus 4. Both of these terms have an x squared minus 1 to the first power at least. And so what do you get if you factor that out? So the negative 4's divide out to 1. This divides out to x squared minus 1. This plus 16x squared, because you're dividing by negative 4, would become minus 4x squared. And this x squared minus 1 has been divided out. And this is now over x squared minus 1 to the fourth. You can reduce this a little bit to the third. I think this is as far as I need to take it to be able to set f double prime equal to 0 and equal to undefined. So f double prime of x equals 0 when negative 4 times x squared minus 4x squared, so negative 3x squared minus 1 equals 0. So the negative 4 doesn't need to be there. So that's when negative 3x squared equals 1. That's when x squared equals negative 1/3. That never happens because if I square something, it can't come out negative. So there's no time where this is equal to 0. And then the denominator, f double prime of x, could be undefined, which can still be an inflection point. That's just where you could have a vertical tangent or maybe a sharp turn. Anyway, f double prime is undefined when x squared minus 1 to the third is equal to 0. And that's just when x squared minus 1 is equal to 0. So plus or minus 1. So then we get these possible inflection points onto the graph, or the number line, I should say, for f double prime of x. And this is going to inform us about what's happening with f of x. Remember, this number line is just a visual for you. You have to actually write out the conclusion using a bit of math notation, so you can't, a grader will not look at this and count it as anything. So I have my f double prime equation, which, let me clean it up even a little bit more. So it's negative 4 on top. I said it was negative 3x squared minus 1. So actually that's 12x. Hold on, I don't want to have false equivalencies. It's actually positive 12x squared plus 4. So the top is always positive. All right, so when we put in negative 2, for example, excuse me, I get 12 times 4 plus 4 over 4 minus 1 cubed. That's a positive over a positive. And if I plug in 0, I get 4 over negative 1 cubed, negative. And then if I put in 2, I'm going to get the same thing as if I put in negative 2, so that's positive. So there are inflection points because the sign of f double prime changed on either side of negative 1 and positive 1. All right, so finally, I want to double check this. Open intervals. Oh, it wasn't asking for point of inflection. Sorry. So concave up or concave down. So f of x is concave up on negative infinity to negative 1 and 1 to infinity. You need to justify or just get in the habit of justifying. So it's because f double prime of x is greater than 0. It's positive. F of x is concave down on the open interval negative 1 to 1, and that's because f double prime of x is less than 0. You should write out the word because on your AP test. I'm just not doing it on my homework. Okay, number 14. This one's kind of obnoxious with the numbers, but the thing here is don't get fooled into doing the quotient rule because this is just a constant down here. So we could just pull a 1 over 270 out if we wanted to. We can't. There is a GCF in here with the x's that we can work on, but we'll deal with that later. So what's y prime going to be? I'm just going to take out this 1 over 270 out here. That might be different than what I did in my answer key to start. And actually, let me just move my work over here so I don't run into what's going on here. All right, so what's the derivative of the numerator then? So it's negative 15 x to the 4th plus 120 x to the 3rd plus 135. And we want the second derivative, so y double prime is equal to, so again, I'm just going to keep the 1 over 270 out here. I don't need to factor that in, I don't think. So negative 15 times 4 is negative 60 x to the 3rd plus, so 12 times 3 is 36 times 10 is 360 x squared, and then the derivative of 135 is 0. And so we just want, when is this equal to 0? So y double prime is equal to 0 when negative 60x cubed plus 360x squared is equal to 0. I don't need the 1 over 270 because I could just multiply it over here. And we can take out a 60, right, or a negative 60. That becomes positive x cubed. This becomes minus 6. We can take out a 60x squared. How about we do that? The greatest common factor, not just a common factor. We can take out a negative 60x squared or a positive 60, it doesn't matter. So this would become x minus 6. And so possible inflection points are 0 and 6. We can get those on a number line. And we can test into y double prime to see where our concave up and down sections are. So this is a cubic, so you could say, oh yeah, it's a negative x to the 3rd cubic, and the multiplicity at 0 is even, so the graph is going to not change signs at 0. It will change signs at 6. Informally, we say like bounce versus cross. Graph goes down on this side, up on this side because it's a negative x cubed. Bounce, cross. Or you can test numbers. You can test -1 and 1 and 7 and see what happens. But either way, it's positive, positive, negative. Now remember, where y double prime is equal to 0, it's not positive or negative. So we are going to split up the concave up section. So y is concave up on -infinity to 0 and 0 to 6 because y double prime is greater than 0, and y is concave down on 6 to infinity because y double prime is less than 0. All right, next problem. Find the points of inflection. That means that we need XY points of inflection and discuss the concavity of the graph. So discuss the concavity will be what we just did before as well. So let's find the second derivative. F prime is 3x squared minus 12x plus 12. F double prime is 6x minus 12. F double prime of x equals 0 when x equals 2. There are no places where f double prime is undefined. Either do this graphically or test numbers. Again, you could test 0 and 3. Or you could just say, oh, this is a line with a positive slope. It's got a 0 here. So negative and then positive. And then because we changed from concave down to concave up for the graph of f, that's a point of inflection, and we can discuss concavity. So I also need the whole point of inflection, so I need to know what f of 2 is equal to. It's equal to 8 minus 6 times 4 plus 12 times 2. So f of 2 is equal to 8. All right, so I'm going to say this. 2, 8 is a point of inflection. You can say POI if you want. The only reason you need for that, if that's all you're justifying, is because f double prime of x changes signs. It doesn't matter that it goes from negative to positive or vice versa. So that's why I know that's a point of inflection. And then they asked me to discuss the concavity. So I will say f of x is, okay, I'm going to start abbreviating, concave down on -infinity to 2 because f double prime is less than 0, and f of x is concave up on 2 to infinity because f double prime is greater than 0. Right? Let's do the same thing for 27. This is a little more complicated of a function. We'll have to use product rule here. And remember, this is x times x plus 3 to the 1/2. So let's find f prime of x first. So I like to do first times derivative of the second. So it's 1/2 times x plus 3 to the 1/2 minus 1, so -1/2. Technically, it's times the derivative of x plus 3. I just like to put that in here while we're doing this early on so that you don't forget about chain rule. It's nice to always be checking that, but you don't have to write that. Plus second times derivative of the first, and the derivative of x is just 1. So before we go taking the derivative again, we need to clean this up. So this is 1/2 x. I'm going to keep the negative exponent because it will probably be in my best interest to factor this a bit. So instead of doing a product rule, instead of taking the derivative right now and doing a product rule plus a power rule, maybe I can get this to just be a product rule. So let's take a look. If we factor out, they both have this x plus 3, and you can factor out the lower of the two exponents. So remember, you can factor out the -1/2, x plus 3 to the -1/2. That would leave you with 1/2 x. plus, and then when you factor or divide in x plus 3 to the negative 1/2 into this, you get x plus 3 to the first. And yeah, we can combine like terms on the inside. So f prime x is x plus 3 to the negative 1/2 times 1/2 x plus x is 3/2 x plus 3. I don't need these parentheses here. I just was showing you it's to the first power. Okay, let's find the derivative of this. So maybe I'll change colors here. So f double prime is first times derivative of the second. So the derivative of this is just 3 over 2. It's not terrible. Plus second. Forgot to write my x there. Times derivative of the first. So this is power rule. Negative 1/2 x plus 3 to the negative 1/2 minus 1 is negative 3/2. Okay. Now, what do we have to look at here? So, okay. I'm trying to look for a GCF. Let me clean it up just a little bit. So I have a 3 over 2 times x plus 3 to the negative 1/2. And then let's go ahead and do this. So minus 1/2. Actually, we can take a 3 out of this too, can't we? Let's factor a 3 out of this set of parentheses. So this is like 3 times 1/2 x plus 1. So now I can factor out, and because of this, I can factor out a negative 3 over 2. And then I still have 1/2 x plus 1. And then here I have x plus 3 to the negative 3/2. So all I did was multiply this times this and pull it out front. And I'm left with this and this. All right, now this GCF is a little nicer. So I've got 3 over 2. They both have this x plus 3. And the smaller of the two exponents is the one that's further down the number line in the negative direction. So I can take out the negative 3 over 2. And what would that leave me with? So negative 1/2 minus negative 3 over 2, so plus 3 over 2. That's now 1, so x plus 3 to the first. And then I factored out the 3/2, so there's a minus here still. This doesn't go anywhere. It's still there in parentheses. And this got factored out completely. This is something I can work with. So I have a 3 over 2 out here. Let's combine terms in here. So 1x minus 1/2 x is 1/2 x. 3 minus 1 is plus 2. And then this 2 could be down here. This has a negative exponent, so let's go ahead and put it down here. All right, and that's enough for me to get to my possible inflection points. So f double prime of x is equal to 0 when 1/2 x plus 2 equals 0. So if you subtract 2, multiply by 2, x could be negative 4. F double prime of x is undefined when x plus 3 to the 3/2 equals 0, which is just when x equals negative 3. So I have two possible inflection points. Negative 4 needs to be to the left of negative 3. I'm definitely not graphing this f double prime. It's not just a nice little polynomial. So I am going to test numbers into this and see how it comes out. So now there is a domain restriction here because this is the square root of x plus 3 and then you're cubing it. So when I go to try to plug in negative 5, for example, I can plug it into the top just fine. But then down here, I get an imaginary number, negative 2 to the 3/2. That's the square root of negative 2. So this whole section is out of the domain. And same thing here. X has to stay greater than negative 3 to be in the domain here. So this doesn't exist on f of x, or on the f double prime graph either. And so then, and same with f of x, sorry. Back here, the domain for f of x is only x is greater than or equal to negative 3. Okay, and so let's just plug in 0. If we plug 0 into this, we get 3 times 2 over 2 times 3 to the 3 halves, positive. So there is no point of inflection because f double prime never has the chance to change signs. So I'm going to say f of x has no points of inflection. And what's my reason for that? I will say because f double prime of x is greater than 0 for x greater than -3. And then they wanted me to discuss concavity. So f of x is concave up on -3 to infinity because f double prime of x is greater than 0. All right. Number 43. Find all relative extrema. Relative extrema are where your graph changes from increasing to decreasing. Use the second derivative test where applicable. So remember, the second derivative test is find f prime, find critical numbers, find f double prime, plug in critical numbers. If f double prime is positive or negative, as long as it's not 0, then you can conclude about relative max, relative min. All right, so f prime of x is equal to 4x cubed minus 12x squared plus 0. Find the critical numbers, so set f prime of x equal to 0. That's when I can factor out a 4x squared, and I get x minus 3. So the critical numbers are 0 and 3. Okay, now find f double prime of x. It's 12x squared minus 24x. Evaluate f double prime at each of the critical numbers. F double prime of 0 is 0, so I can't use second derivative tests. That's annoying. F double prime of 3 is 12 times 9 minus 24 times 3. So, what would this be? I could do 12 times 10 and then subtract a 12 if I want to do it that way. Do I want to do it that way? That's not making my math any easier. 108. Okay. Or I could just do 12 times 9, whatever. Minus 1272. So positive, that's all I care about. F double prime of 3 is positive. Okay, so I can use second derivative test at 3, but I can't use second derivative test at 0. So it's kind of silly. I don't use second derivative test most of the time unless I'm told to, because it doesn't always work, but first derivative test always works. So I can say this, because f double prime is greater than 0, I still have to sketch this for myself. It means that there would be a relative minimum happening because the graph is concave up. Graph of f is concave up here, so there's a relative min. I know there's a horizontal tangent in concave up. So I can say find all relative extrema. So f of 3 is a relative min because f prime of 3 equals 0 and f double prime of 3 greater than 0. That's all that you have to say. You don't have to draw the picture. You don't have to explain what's happening. That's it. So that's by the second derivative test. But for this one, I have to use the first derivative test. So I have to say, well, what's happening with f prime on either side of 0? So f prime was 12x cubed minus 4x squared. You can just plug in -1. You get -4 minus 12 times 1. That's negative. What if you plug in +1? You get 4 minus 12 times 1. That's also negative. So there's no relative extrema because at 0, because f of x goes from decreasing to decreasing still. It's one of those that looks like this, probably. All right. So no relative extremum at x equals 0 because f prime of x less than 0. Or how about this? Doesn't change signs. That's a bit more specific than just saying it's negative. Okay, same thing on this one. So, we have trig, and we're on this interval here. So, all right, so let's find f prime of x. So the derivative of cosine is negative sine. The derivative of minus x is minus 1. And then I can find critical numbers. Now this one, the negative sine graph looks like this. Remember, the highest it reaches is 1, and then this is shifting it down 1. So now it's like the midline is negative 1. It goes like this. So f prime is always negative. Whatever. Let's just go ahead. Okay, so when is this equal to 0? Sorry. F prime of x, find the critical numbers. When is that equal to 0? That's when negative sine x equals 1. That's when sine x equals negative 1. We're on 0 to 4 pi, so this is 2 full circles. We need to give 2 answers here. So the first time in the first unit circle where x is equal to negative 1 is when x is 3 pi over 2. That's only 1.5 pi. You have to get out to 4 pi, so add 2 pi to that, and you get, not 5 pi over 2, you get, add 4 pi over 2 to that, you get 7 pi over 2. Because remember, 8 pi over 2 would be 4 pi. So 1.5 and then an extra circle around. These are the critical numbers. And then we need to find f double prime of x. So what's the derivative of this? So the derivative of negative sine is negative cosine x, and the derivative of negative 1 is 0. Evaluate this at both of these numbers, and second derivative test fails because cosine is 0 at both of these coordinates. So can't use second derivative test. That just means we go back to the first derivative test. And whether you sketch the graph or not, you're getting, I think sketching the graph is a good idea because it saves you from doing like trig stuff. But this is negative all the time. So f prime negative sine minus 1 is negative, negative, negative for that whole thing. So you can plug in numbers if you want, but I don't think you need to. So the question was going back to relative extremum. So there are no relative extrema. This time I'm talking about max or min. On f of x, because f prime of x is always less than or equal to 0 on 0 to 4 pi. Really for all real numbers, but on our interval of interest. All right, let's look at these 2 problems. So consider a function f such that f prime is increasing. Now, if f prime is increasing, if something's increasing, it means its derivative is positive. So that means that f double prime is greater than 0. That means that f is concave up. Sketch graphs for, okay, so for part A, we have f prime is increasing, which tells me that the graph is concave up. And this says f prime is less than 0, which tells me that f is always decreasing. So I need to draw a graph that's decreasing and concave up. So, and that's, we're just assuming it's defined everywhere. So here we go. Concave up but decreasing, maybe like an exponential, decay graph or something. That's my graph of f. For part B, we want f prime to be increasing. So again, still concave up. But this time it says f prime is greater than 0. So that means that f is increasing. So concave up but increasing, I'm just going to draw like an exponential growth graph. All right, for part B, consider a function where f prime is decreasing. So f prime is decreasing. That tells me that f is concave down. And sketch the graph for part A, where f prime is less than 0. So f is decreasing. So decreasing but concave down. So decreasing but concave down would be like something like this. And then for part B, f prime greater than 0. So I need f to be increasing, but still concave down. So these are like log graphs of some sort. Right? The graph of f is shown. Graph f, f prime, and f double prime on the same set of coordinate axes. So I'm just going to draw them right on this graph here. So if you need to, you can resketch f. The derivative of f is linear. F is linear. So the derivative of f should just be the slope of this line. So what is the slope? It goes through 0, 1, and negative 1, 0. So this slope is 1. So the derivative of f is a horizontal line. So that's f prime. And then what's the slope of the f prime graph? That is 0. So f double prime goes through 0. All right, now we have some graph sketching. We're going to do more of this in a packet, I think, tomorrow. So sketch the graph of a function having the given characteristics. So always begin by plotting the points they give you. So we have to make sure that f of 2 is the same as f of 4, and they're both equal to 0. So 1, 2, 3, 4. F of 2, f of 4, those are zeros. F prime of x is less than 0 if x is less than 3. So f prime of x, so f is decreasing to the left of 3. So something like this. And then f prime of 3 does not exist, so that could be like a horizontal tangent, no, not a horizontal tangent, sorry. That could be a sharp turn. Or it could be a vertical asymptote. F prime of x is greater than 0 to the right, so f needs to be increasing to the right of 3. So decreasing to the left, increasing to the right. And the second derivative is less than 0 as long as x is not equal to 3. That means that the whole graph is concave down everywhere. So concave down decreasing, concave down increasing. So I think I am going to do a sharp turn at 3. So I'm just going to do something like this. Zoop, and then a sharp turn, deep. It's supposed to be curved the whole way. You could also do a vertical asymptote at 3. It doesn't say f has to be continuous. So you could also do a vertical asymptote. All right, let's see. For this graph, let's plot these points. F of 0 is 0, and f of 2 is 0. F prime is greater than 0, so f is increasing if x is less than 1. So f is increasing. F prime of 1, is equal to 0, so I need a horizontal tangent. So at 1, there's some sort of horizontal tangent. F prime is less than 0, so f is decreasing to the right of 1. So we're going to be decreasing to the right of 1. And then f double prime less than 0, concave down again. So concave down, concave down. So like a parabola, something like that. Right? We have this little horizontal tangent here, increasing then decreasing, concave down the whole way. Okay, last graph to sketch here. F of 2 is equal to 0, and f of 4 is equal to 0. F is increasing if we're to the left of 3, so increasing. And then f prime of 3 does not exist. That needs to be, again, sharp turn or vertical asymptote at 3. F prime is less than 0, so f is decreasing to the right of 3, something like that. And this time we need to be concave up, so doop, doop. All right, so again, we can do something with a cusp like this, a sharp turn, or we could do a vertical asymptote through there. Doesn't matter. All right, 72. Part A, graph. F of x equals cube root of x and identify the inflection point. So that's easy, I think, right? So we're just graphing a parent function that we already know. Goes through 0, 0, goes through 1, 1, negative 1, negative 1, goes through 8, 2, negative 8, negative 2, does one of these. Definitely seems like there's an inflection point at 0, 0. Point of inflection, 0, 0, because we're concave up, and then we switch to concave down. Does f double prime exist at the inflection point? So we could find f double prime and show that it does not exist, but you're going from slopes that are close to 0 to more and more positive, and then they start tapering off. They're still positive, but they get back to 0. So the closer you get to 0, the higher this number gets. So f double prime of x does not exist because there is a vertical tangent right here. The slopes just get steeper and steeper and steeper until they hit their tipping point and turn over. So because there is a vertical tangent at x equals 0. You could also find f double prime of x, and it will have an x in the denominator for which it is undefined. Okay, true or false? The graph of every cubic polynomial has precisely one point of inflection. So cubics, we're used to them being like that, like, oh yeah, that would be one point of inflection, or like a boring cubic still has one. We could do this. I think this is true, but we could do this a little more formally. Let's just show. Let me recharge my pen here. Let's come up with a generic cubic equation, like f of x equals, I don't know, some ax cubed plus some bx squared plus cx plus d. I don't know what the coefficients a, b, c, and d are. They can be any real number. So then what would f prime of x be? It would be 3a x squared plus 2bx plus c plus 0. And we're talking about points of inflection, so let's take a look at f double prime. That would be 6ax plus 2b. So f double prime would never be undefined, but it would equal 0 when x equals negative 2b over 6a. And so that's only one solution for the point of inflection. And this is linear. So on either side of its 0, it has to change signs. So yeah, I'm convinced this is true. It's going to change concavity at the one place. There will only ever be one place where the second derivative is equal to 0. Okay, 92. The graph of f of x equals 1 over x is concave downward for x less than 0 and concave upward for x greater than 0, and thus it has a point of inflection at x equals 0. I'm not even going to worry about if the concavity is correct or not. Is it correct or not? Yeah, I guess it is. Okay, the concavity is correct. They're not trying to trick us there. But we have to be careful. Just because you change concavity doesn't guarantee that you have a point of inflection, because what's wrong with this picture? F of 0 is equal to 1 over 0, which is undefined. This is false because f of x has a vertical asymptote at x equals 0. So it can't have a point on a vertical asymptote. 93, f prime of c is greater than 0, and if that's true, then f is concave up. The first derivative does not go with concavity, so that's false. All we can say about f is that we know it's increasing at x equals c. And f double prime of 2 equals 0. If that's true, then the graph of f must have a point of inflection, so that's false as well. Because remember, that's just the first step. That's what you then put on a number line and you have to test. So just because you have a possible inflection point doesn't mean that the graph is changing concavity. So not guaranteed that f double prime of x changes signs at x equals 2. All right, this is kind of a long assignment, right? So thanks for hanging in there with me. Come see me if you have office hour, or if you have questions in office hours, please.